Hello, my name is Andy Manoske and I'm a Principal Product Manager at HashiCorp, and yes, you pronounced it well, Dominique. I know that I always say my name is just Andy, but my name is Andy Manoske and it was well pronounced. And here we're going to talk about protecting workflows and secrets. So a little bit about who I am. I joined HashiCorp in 2016 at a stage in the company where we were starting to begin to sell Vault Enterprise. And part of the reason why I did that is that I've spent most of my career in and around encryption, cryptography, and really how we protect secrets as a whole. Here at HashiCorp, as a principal product manager, I focus on how we build products and kind of like think about platform security and cryptography throughout the rest of the HashiCorp Secure Products group. And before HashiCorp, like I said, I've spent most of my time in and around encryption and security. So I formerly led product security encryption at NetApp, as well as worked on the research side at Alien Vault, where I supported the labs team and led development of something called Open Threat Exchange, which is a kind of popular way that security researchers and teams try to collaborate to over open source information to think about how we protect sensitive information and as well as like interrogate cyber attacks. Kind of fun fact there, one of the products that I worked on, Open Threat Exchange or OTX, was one of the tools that was used to attribute North Korea in the state-sponsored cyber attacks against Sony Pictures in 2014. So again, it kind of highlights the fact that, over the course of my career, I've been just basically trying to focus on how we protect secrets, and in particular, how we make it easy to protect secrets. Because when we think about software that's used to protect secrets, there's this quote that always strikes me from one of our Vault Enterprise users, which is, in her opinion, the best security tools are the ones that you actually use. And this kind of rings true for the fact that, in 2020, we have a number of different ways to protect information, using very complex mathematics, using very complex tools to detect adversaries, to stop adversaries as they're kind of in the process of attacking a system. But there seems to always be this kind of trade-off that hasn't changed since the very beginning of information security and cryptography, which is as I apply sort of security tools and security protections, that I'm simultaneously also challenged by the fact that there's like a cost to it, the cost to usability and the cost to, how I might impede a workflow. And this is something that we're really keen to focus on with Vault because, as we introduce new features into Vault that really focus on protecting secrets and, defending information, we need to do so in a way that doesn't hinder the ability of practitioners, developers, and really anyone that's, a constituent Vault user, whether they know it or not, to be able to conduct the workflows that they are engaged in. So let's kind of step back for a moment and talk about how we at the Vault team think about the world. We take an adversary modeling approach to thinking about how we build Vault and Vault Enterprise. And what I mean by that is that we try to step back for a moment and think, okay, what is going on in the world? And in particular, what is going on to motivate adversaries? Well, unfortunately, the world is kind of in a very complex situation, and not just because of what's going on from COVID-19, but certainly that does not help things. Even without the pandemic, there is a significant amount of complexity that's going on in enterprise IT and enterprise infrastructure. That complexity is challenging because if you've spent time in information security, you know that complexity is sort of the enemy of security. The more complex a system is, the more likely that someone can circumvent that system or exploit aspects of that system to be able to launch complex cyber attacks that can circumvent cryptography. In 2020 alone, the number of passwords that are used by machines and humans are expected to exceed 300 billion. And that kind of highlights the fact that security infrastructures in 2020 are very, very complicated. Especially when you look at the enterprise, where the enterprise is, and we define the enterprise here in HashiCorp as really the global 2000. Within these kinds of users and environments, you typically have multiple or even redundant infrastructures of security, redundant firewalls, redundant types of defenses. And on one end, this makes sense. There's a model that we frequently talk about in security called the defense in depth, which focuses on kind of like, let's think about your infrastructure like it was a castle. So I have different concentric walls that are built in such a way that if someone breaches the first wall, they can get in and they're faced with another wall that they have to breach. Now, this makes a lot of sense, and defense in depth is generally speaking a good idea, but in challenge, the complexity that breeds there, and especially in terms of creating lots of different types of credentials or other secrets that I need to protect, is a significant challenge. The second kind of motivating factor here that's complicating things is, like I said, adversaries. The style of thinking that, I am facing a bunch of kids that are basically breaking into me for fun, sort of like the hackers movie style like approach of cybersecurity does not really apply here. When we look at the global 2000s, 71% of breaches were financially motivated and 25% were motivated ultimately by espionage. So, the modern enterprise is not facing, Dade Murphy and Zero Cool and the rest of his friends. They're facing, organized crime. They're facing state-sponsored adversaries that are ultimately there to commit espionage on, privileged information that they have. They're facing, phishing rings, mercenary hackers hired by governments, etc. So, you're not facing simple adversaries. You're facing complex adversaries, and these advanced adversaries are ultimately motivated by the need to conduct very damaging attacks. And ultimately, the consequence of these damaging attacks are data breaches. We've all heard about data breaches, especially within the European Union. There are consequences for data breaches in the form of the GDPR. But when we break down and analyze the statistics of what happens in most data breaches, especially in the last year, we see some very troubling trends. First, when it comes to 2019, there were around 4,000 data breaches that were at least logged, and there's obviously probably a significant amount more that were not logged, but this is a significant challenge for the goal 2000. Around 4.1 billion plus records at least were exposed. Now remember, with GDPR, every time I expose a record here, I'm committing an infraction against GDPR, and the implications of that infraction, depending upon who your supervisory authority is within the European Union, can be very significant. So, with 4.1 billion records exposed, this has the potential to potentially cripple some companies based off of the infractions they face for having been suffering these data breaches. 72% of the targets were the enterprise. And again, this makes sense, right? When we look at sort of adversary modeling here, the adversaries we're facing are not kind of kids poking around, blowing up websites for fun necessarily. They are motivated professional cyber attackers, hackers who are trying to steal information ultimately for espionage or for financial reasons, to sell on the dark web, etc. And to highlight this, the victims of their records being breached online, 58% of those 4,000 have had resulting attacks. So, if your data was breached online, you have a non-trivial possibility that it was then consumed and used to commit identity theft, to commit fraud, etc. And this really highlights that when it comes to facing cyber attacks, this is not a victimless crime. This is a very challenging sort of enterprise that is going to get only worse for the Global 2000, complicated by the fact that, as I move towards digital adoption, especially in the case of COVID-19, I now incur more complexity, and I might be forced to confront these really advanced adversaries online who are after my information, but without the capabilities to defend myself because I'm various types of lockdowns and restrictions for, in-person contact, in-person business, etc. So how do we deal with this problem? Well, in Vault, we typically look at how we protect data in two ways. And first, let me kind of go back and talk about what is a secret, because you hear this term a lot when it comes to Vault. Well, a secret is anything you don't want to be public. A secret can be, for example, a phone number, a credit card number, a tax ID number, a social security number, a FIN number, etc. These are all pieces of information that can be effectively referenceable by a string, but these are all sensitive things that you don't want to get out. And they could be things that you don't want to get out because of regulations like GDPR. There could be things that you don't want to get out because they're not necessarily bad, they won't trip GDPR, but you just don't want them to get out for reputational risk reasons, or because it could lead to another person kind of advocating conducting a kind of cyber attack or anything else like that. It's just something that you don't want to be public. And this is really important because when we step back and look at why Vault was created, one of the reasons why we built Vault in the first place was to really make sure that you don't have to face this dilemma of what secret is secret enough that I have to protect it? What secret is so important that I have to kind of weigh the challenge and cost of how do I protect this information versus how hard it is to deploy a system to actually protect it? With Vault, the goal is for you to never have to make that judgment. You can just protect it no matter what. You never have to deal with sort of the complexity of deploying cryptography, etc., unless you want to. So the most basic way to protect any of those secrets is what we call the KV secrets engine, or the key value secrets engine. There's another way to protect secrets also, which is to make sure that that secret never leaves Vault. Now, when I protect something in the KV secrets engine and I use features within Vault like dynamic secrets, this doesn't necessarily require that I, for example, pull it out of Vault. When I leverage the ability to access these secrets in Vault, I'm getting a token that allows me to, provided I am with SAM, I've authenticated myself properly, etc., I can go in and request that secret. And it only gives me access for a very short bespoke period of time, something that we call dynamic secrets within Vault. But let's say that I don't want users to access the secret at all. And this kind of highlights sort of a lot of trends that we're seeing in security around zero trust, around the ability for a user to ultimately hold on to data that isn't sensitive by nature, something that couldn't be used to privilege escalate or otherwise compromise their infrastructure. In Vault, we consider this being called orchestrating a security workflow. And there are secrets engines within Vault, mechanisms for you to be able to use a secret stored within Vault to conduct an operation where the user is actually not getting access to the secret, but Vault is sort of handling what the user was intending to do. So let's go with a good example. Within Vault, I have a KB secrets engine where I could store something like an AWS secret key. An AWS secret key could be used by an application to be able to call something within the AWS API. Maybe I want to deploy an EC2 instance, or I want to go size up my S3 environment. Totally fine. But maybe I don't want to give the user access to my AWS secret key, right? Like, what if I'm concerned that there's an adversary waiting there to compromise something on the user's side to be able to leverage the access to that information, however instantial it may be, to be able to access something within their infrastructure? And unfortunately, in the last 10 years, we've seen attacks like this. We've seen attacks where advanced malware has snuck onto systems, and that malware is able to uses either key loggers or other kinds of mechanisms to be able to circumvent the cryptography of sensitive like secrets management suites to be able to kind of see what the user is seeing and steal it there. This is, again, like, we're not facing we're not facing like teenagers with like hacking kits necessarily. We're facing complex adversaries with the ability to pull off some of these complex cyber attacks. So maybe it's better instead to allow us to be able to make sure that users don't hold on to any sensitive information at all. So instead of using that, like saying, hey, let's go give you access to that secret key for my entire infrastructure, how about instead I give you a credential that is dynamic, that is created just for this time, that's going to only live for something like 30 seconds, and if someone steals it, it won't give them undue access to my infrastructure. I can't conduct privilege escalation or otherwise use something that's been misconfigured within the access control rights for that credential to be able to like escalate what I should be able to do as an adversary, which is a complex, mechanism, but something that we've seen throughout many of the like large data breaches in the last 10 years. We have secrets engines within Vault, like the Database Secret Engine or the AWS Secret Engine, to be able to allow you to create these dynamic credentials. And in the case of if I wanted to go call something within the AWS API, there's an AWS Secrets Engine that is specifically created for the purpose of creating IAM roles. So a user or developer can then go do whatever they need to within their infrastructure. And you, as the operator who is managing Vault, can ensure that that workflow only is provisioned for a specific user, only is conducted for a specific specific kind of like task. So for example, they can't call things that they shouldn't be able to call because that IAM role doesn't have the rights to be able to do that, etc. So this is kind of the dichotomy that we see in Vault today. Protecting a secret, where I have a secret completely stored within Vault and I'm gating access to that secret for users just for like the just-in-time access to it. Or I'm ideally orchestrating a workflow. So I don't access that workflow at all. I don't have users accessing any of the secrets at all. They just it's an opaque process where I get a non-sensitive piece of information because it dies really quickly after that, or it's really explicitly scoped to a specific role or task, or ideally both. But what happens if the data doesn't live in Vault? And this is kind of one of the challenges that over the course of the last 5 years or so we've been trying to contend with. Vault is very, very good traditionally at protecting data that all lives within it. But like we talked about at the very beginning, the best security tools are the ones that you actually use. So we think about how we protect external secrets where someone is not going to necessarily store that secret in Vault, either because it's too big, or it's too complex, or the workflow is something you can't evenly orchestrate. We need to go solve that problem. And let me give you a few good examples for kind of external workflows where I'm not going to store everything necessarily within Vault, or the orchestration of that workflow is too complicated to kind of like fit within the context of one specific secret engine. So if I want to protect hardware keys for hard drives, this is something that is typically done through full disk encryption. And if you're unfamiliar with the term full disk encryption, or FDE, this is the ability for a large enterprise scale array, or even like laptops, like if you're using BitLocker or something like Veracrypt, to be able to encode a encryption process into the process of mounting that drive, such that if you were to remove that drive from that computer, it doesn't have the ability for that computer to access that information. If I was to like rip out the hard drive right now for my computer and go plug it into another computer, it doesn't have the ability to access it because I've encrypted that drive. So that's what's called full disk encryption. When we look at enterprise storage arrays, they are typically bundled in such that there are, dozens, if not hundreds of hard drives. So if I want to be able to manage all of that information at scale, if I imagine that is one shelf and I have potentially dozens or hundreds of shelves, we're talking about a lot of keys and a lot of encryption. The challenge with that is managing where all those keys live. Now, I could, write a plugin into Vault potentially that does it for one instance of it, but there are dozens of different types of ways to interact with full disk encryption suites. I can either interact with them at like the software level within the computer, kind of like how BitLocker works, and then each of the enterprise storage vendors, the Dell EMCs of the world, the NetApps, the HPs, etc., all of them have different ways fundamentally for you to be able to access how I go and store those keys in the cloud or on-prem or a combination of both. That's complicated. And that's a workflow where I need to figure out one way to kind of like protect all of that doesn't ideally involve creating dozens of different types of secret engines specifically for each vendor. Another one, what if I want to protect credit card numbers in databases? Well, there's a lot of regulations around that. As I'm sure probably many of the people watching understand, there's something called PCI DSS, which is a regulation suite that focuses heavily on how do I protect all the credentials information that comes out of a credit card. Well, I mean, if I need to protect all of that information with strong cryptography, that's great. But every time I deploy strong cryptography, I need to deploy even stronger key management. So what happens if I have hundreds of credit card numbers? Well, I have a lot of data that's trapped within a credit card. I have the Stripe data that's associated with it. I have like the CAN information, the account number that's linked to it. So for example, if I have a debit card, that account number could be a bank account. If I have a credit card, it'd be a credit account, etc. These kinds of challenges are very complex to deal with, and they highlight sort of that explosion of secrets that I need to manage, or what we call within, the InfoSec community, well, that's just a lot of data. Basically, we need to protect a lot of information for each credit card. Now, what happens if I have thousands, hundreds of thousands, millions of credit cards? Now I have a combinatorial explosion of data that I need to manage. Okay, am I going to store all of that in Vault? Maybe, maybe not. Maybe there are times when I need to have some of that data protected within a database. It's more resident to my application, because when someone swipes their credit card going into their favorite retail store, they don't want to wait there for necessarily 10 to 15 seconds just for the initial transaction to occur. There are a number of times where similar types of data that need to be protected outside of Vault need to occur because they can't incur the impact of kind of, storing that data within Vault, or because the scale and size of that data can't necessarily be stored in Vault's storage backend mechanisms. And Vault is a very efficient system. I think one of my favorite examples of this kind of efficiency within Vault is the fact that, we have right now a Vault Enterprise user who is replicating data that needs to be at the sub 3 millisecond range globally. They have interactions where Vault is serving as the cryptographic backend for some very serious financial services applications, and Vault cannot fail, because if Vault fails, it takes out the world economy. That's challenging, and they manage a lot of information through that mechanism, but simultaneously the same underlying subsystems protect a user where they don't care about speed. Instead, they care about the data actually being kind of permissible and accessible and the same between a data center within New Zealand and then a constellation of satellites that flies over. So in that model, 500 milliseconds round trip delay is a pretty good day. If it was the other user, it wouldn't make sense. But sort of the fact that you can have the same subsystems for one kind of user and the same other subsystems for this type of user highlight how scalable Vault is. But there are limits to that scale. There are limits to that scale in the terms of the storage that Vault needs to back up. And so if I really need to have a system that backs up that information in such a way that I can protect that information, that it's referenceable and secure and also accessible to users, sometimes I need to store all those in external databases, and I can't store them necessarily within Vault. So again, in both of these use cases, we highlight challenges with external workflows where there might be an orchestration suite that needs to happen across a lot of other different types of application platforms, or maybe I just need to store too much data, the data that is outside the scope of Vault, and it just grows too fast, or it needs to be located external to Vault for the purposes of application referenceability or speed. It just is what it is. And so if we want to protect these existing external workflows, this has been a focus of the Vault team for probably around 2.5 years. And the result of this is the Advanced Data Protection Suite that you see within Vault Enterprise. The Advanced Data Protection Suite, or what we call ADP within Vault, is really a module that focuses on protecting these external secrets and workflows, situations where I can't necessarily protect everything within Vault, and I need to have Vault go out and intelligently work with an existing workflow, or try to focus on how does it not compromise a developer or user sense of applications, but enable them to act with security in such a way that they don't need to have a deep background in cryptography or ultimately code in a lot of security infrastructure themselves. So let's talk about things like full disk encryption and those kind of existing workflows where Vault really needs to serve as an external key manager, but doesn't necessarily want to do it for dozens of different types of bespoke secret engines to manage. For these types of enterprise protocols, we leverage the KMIT protocol, or the Key Management interoperability protocol to allow us to be able to ensure that if we're doing something like full disk encryption, that the way that Vault does it for one vendor is the same for many of them. And KMIP is a protocol that was created about 15 years ago to be able to allow traditional hardware security modules to be able to conduct these kinds of external workflows where they don't want to, authoritatively interject themselves in an aggressive way that would compromise the ability of applications to leverage that infrastructure. But at the same time, if I am NetApp or if I am, Dell EMC, I don't want to necessarily be in the business of trying to build bespoke key managers. I respect that you have some kind of security management infrastructure on the outside, and instead I want you to leverage that. So it's a way for them to kind of all work together, regardless of the different ways that different vendors kind of think about storage. Same thing was with transparent database encryption. So TDE is a mechanism that allows you to be able to have a different database protect itself by encryption and manage those keys offsite in some other kind of location. So when we look at TDE, there's a lot of different databases out there in the world, obviously. MySQL, MS SQL, pretty much everything that you can think of that is web scale cool and also like non-relational. And, they all have different ways of implementing encryption to be able to protect them. But the one thing that they all kind of agree on is the fact that, hey, I need to have a key manager somewhere to protect this information. So for TDE, many kinds of databases leverage KMIP to be able to enable these kind of processes where that external key manager exists. I say, hey, look, I might be MongoDB Enterprise or I might be MySQL. It doesn't matter. I know that I need to store this key offsite. So KMIP is a really good protocol for us to be able to leverage to allow Vault to exist as a KMIP server. And this is part of the ADP platform for that reason. We want to be able to build you functionality that ultimately doesn't require that you kind of like authoritatively interject or disrupt an existing enterprise protocol or enterprise workflow, because again, you want to use secrets and security management tools that you actually use. Otherwise, it's all for naught. So that's good from the protocol perspective. But what if there is no protocol? What if there is no mechanism for you to be able to leverage to automate that process, the key management process or that secrets management process for your existing workflow? And what if we run into that problem of like the credit card number problem where I've got a lot of data that needs to be protected, but that data needs to be protected in such a way that it resides, that it resides outside of Vault. That's where we start thinking about, okay, let's kind of go back to the drawing board and see how cryptography in general tries to address this problem. Well, in cryptography, one of the primary ways that has been seen to interject this is tokenization. And this is kind of the first approach that the Vault team took a look at when we were kind of trying to figure out how do we protect external secrets that live outside of Vault. For those of you that are unaware what tokenization is a process where you generate either a random or otherwise one-way referenceable identifier for information. So whether that information is a credit card number, social security number, again, pretty much anything referenceable as a string, I can identify it in a one-way transform. And I protect the mechanism that's used to be able to ensure that a user or an application can say, here is my unique identifier. I want to go back to a system that's external to me and say, hey, system, here's an identifier, here's my credential or my identity, give me back the information. We typically, at least the industry is typically trying to challenge that with a cryptographic hash as a way to implement this kind of system. And a cryptographic hash is a little bit different from what you might see as a programmer with a normal hash algorithm. And it's not necessarily because there's any encryption that goes on within it. Instead, the cryptographic here refers to the fact that there are minimal to no collisions possible, at least with any kind of like known constraints of data. And a collision is the ability, for me to hash one set of data. So if I was to hash Andy and I get back 1, 2, 3, and if I was to then hash something like Manoske and I get back 1, 2, 3, well, that would be a collision. That would be I have two identifiers that come in that are hashed that ultimately resolve to the same kind of hash value. Now, why is that bad? Again, on the Vault team, we don't think with kind of the focus of like just how do I build cool security tools? We think about this of like an adversary. And when we think about how an adversary thinks, if I'm going to use something like, if I'm going to attack a system like tokenization, I'm going to employ some kind of mechanism to be able to ensure that I can go around the security, employ what's called a side channel attack. So a common side channel attack on tokenization, other than just breaking the system or exploiting a vulnerability in it, is to run what they call a rainbow table attack. Now, a rainbow table attack is really where I have a system of pre-computed hashes and I steal some kind of like credential or like a salt or an identifier for those hashes, and I run checks to see like, hey, if I've stolen a cryptographic hash, or like if I know sort of what this tokenized value is, I'm going to go see what it maps to. given if I know the algorithm and I know sort of like this other kind of key detail, I can probably search through that list of common, passwords or common identifiers, etc. So if I'm doing tokenization, it's really important that I have some kind of cryptographic hash algorithm or other kind of like mechanism to be able to ensure that making that process of searching for a unique identifier is as difficult as possible. So once I've done that, assuming that like I've deployed tokenization, I store that secret within an external database, and then I protect the hash input table. For those of you that have a background in cryptography, this really means that I'm holding on to what's called a one-time pad encryption. I've got this kind of like table that is hopefully non-referenceable, that is not reversible in the case of tokenization, and I protect it, and I really, really hope that an adversary isn't able to breach my system to be able to take a look at that table, because otherwise they've got to contend with mathematics. They've got to contend with the difficulty of searching for possible inputs to that. And we can make that really hard using math. And it highlights, again, sort of one of the things that we always want to do with Vault. We always want to push people towards cryptography so that they have to fight that as opposed to fighting the entire system. Because unless they've got, sufficiently advanced computers, that's going to take, one of my favorite terms as a crypto person is longer than the heat death of the universe to be able to actually search for. So we want you to be searching for longer than the heat death of the universe to be able to search for things. And most tokenization suites want you to do the same thing. But there are challenges to tokenization, and it's one of the reasons why our first approach to this is not going to be tokenization, or was not. First, the most important one, the data is not preserved when you tokenize something. So if I'm properly tokenizing a value, that data is not going to retain the same format. ABC123 might come out to look something like gobbledygook, anything that's like in UTF-8. And that challenge is really because I don't want that to be reversible. Again, there shouldn't be anything necessarily deterministic about how ABC123 is resolved, so that it makes it really difficult for that adversary to run a rainbow tables attack against it. We want to make sure that, it's really challenging to deal with that cryptography, to go around the cryptography. So, I'm going to generate a fully random output ideally from that data. Unfortunately, that means that I'm going to inherently destroy the underlying formatting of that data. So format preservation goes out the window when we talk about tokenization. And that's bad from our perspective, at least from like what we're trying to achieve, just because, when we want to build systems again, we want to build a system that you're going to use. And if I'm going to make it more complicated on top of the complexity that you're already facing, that's not necessarily a good thing. So if we're going to go build tokenization, we're going to do so really as kind of like the second ideal here, because we don't want to include and introduce more complexity to your system. We want your developers to be able to make, your data management as simple as possible, even if you are using Vault as a mechanism to protect that data. Finally, the space complexity. This is a big problem. When I am protecting data with tokenization, again, I am building a one-time pad, effectively, of all of the mappings of that data. I need to know how ABC123 becomes pound, $, squiggly face. And if that's the case, that means that I'm copying that data effectively. So, think about what some of the challenges that we were facing before. One of the challenges is that the data is necessarily too big or was like scaling too quickly, or otherwise, for some other reason, performance, etc., can't live within Vault. So the data can't live within Vault. It's probably going to trip over the same kind of like space complexity challenges that we're going to face. So, this makes tokenization a non-ideal first approach to this problem, because the challenge with tokenization is that it trips over the same kind of things that we don't want to trip over in the first place, which is, we make it harder potentially for users to leverage that information, and we challenge sort of the complexity associated with your existing system by making it harder for you to protect that token table. Okay, so what did we do instead? Well, our first approach then is Format Preserving Encryption, or FPE. And specifically within a secret engine that was released in Vault 1.4, the Transform Secret Engine, you can leverage FPE to protect data and also make sure that the data is encrypted. So why did we choose FPE? Well, first, FPE was the first mechanism that we chose to preserve this data because it preserves the data type, something we call data type preservation. We don't destroy the underlying formatting when we protect the data. So for example, if you're looking at this input here, I can make sure that there are dashes in the right places. I can make sure that there are 4 digits for each kind of like style of input. And the output looks like something that is the input. It looks like the same data type. And that's really important. That's really important for a few reasons. First, again, we expect that in this kind of like set of protections that we're going to store this data outside in some kind of like, potentially format limited or format preserving data system or data structure. So a really good example of this, a database. If I'm going to store it in a database, there's a schema associated with the database. If I want to store that data in a way that is, compliant with the schema of that database, I need to, protect that information in such a way that it's going to look like that data information. And that's great from a, data management perspective. If I'm using a relational database where schema is very important, this is a very valuable kind of feature, but it's also very valuable in kind of other aspects. Like, for example, if I'm using a file system and I don't want to make the variable, like, you know, the size of the data variable such that it could like compromise what I would think is like the size of a file, that's also very important. If I want to limit the size of it, etc., this is really important. We also see format preservation and data type preservation very important when it comes to managing you know, text and character sets that is outside of English. So UTF-8, which is the common character set that we use within Vault, and also within most parts of the world outside of simplified Chinese and Japanese kanji. These are challenges that, you know, this is a character set where I might accidentally kind of like violate not necessarily the schema of that data or the size of that data, but I might make something look like it's not supposed to. I might try to write something accidentally in, let's say, katakana or hiragana that might come out in such a way that it compromises, you know, an application's ability to read that data. If my application is expecting to get only kind of like, let's say, you know, English text, and suddenly I'm dealing with like UTF-8 identifiers that are not English, well, that could be a challenge. And so that data type preservation is very important, not just necessarily just for like scale or size or, you know, the schema associated with the database, but also really for an application's ability to consume that information, to store that information, and ultimately when the time comes to swap it. Now, second, one of the reasons why we chose FPE was this changes the scope of the problem. You're no longer focusing on like, how do I protect that kind of like data, you know, that one-time pad, that association of random tokens to identifiers. That is a worthwhile problem to take on, but instead we focus on this as a key management problem, which is something that Vault is very good at already. By focusing sort of FPE into a key management problem, we ensure that we're not storing a copy of that data, so we instantly cut down on a lot of the data that we have to store, and we ensure that it's a lot, you know, there's less data that you have to manage. And again, the whole point of one of the things that we're challenging with is the fact that data is complex, my infrastructure is complex, and just getting more and more complex. So we want to like reduce the amount of information that you have to protect, reduce the amount of data that you have to manage. And FPE is very, very good at that because we can protect the data that lives within Vault in such a way that it's just like another key management problem to Vault. And you can ensure that you're not copying and placing more copies of that secret data outside or managing another external system storage data. So how do we do that? So we use the AES FF3-1 algorithm. Now that is a lot of acronyms, and where I am right now in San Francisco at 4:30 in the morning, that's just a lot of gobbledygook. So let's kind of dive into what is FF3-1. There is a document called the SP800-38 Golf series, which is the security special publications for security documents that is released by the U.S. National Institute of Standards Technology in collaboration with the Canadian CSE. And what this is this is basically a bunch of like academic documents that guide users and security professionals on how they should implement protections. 38 Golf is a document that focuses specifically on how do I implement format preserving encryption, and AES FF3-1 is a specific encryption algorithm that is mentioned in that document and analyzed as a mechanism to do that. How does AES FF3-1 provide this capability for you to encrypt data while at the same time preserving its specific alphabet, which is those characters that we talked about, whether it's Latin characters like Japanese hiragana, Arabic numerals, etc. Anything that's basically within a specific character set. It can preserve that character set, and it can also preserve the formatting. So there are, it's a certain number of characters, and then I'm going to include a dash or a pound sign, etc. So it does this through a combination of Feistel networks and AES XSTS transforms. So a Feistel network is basically kind of like a divide and conquer problem. I'm going to divide up the plain text that I want to go encrypt, in this case, into repeatedly halved solutions. So if you have a background in algorithms, for example, if you study computer science, you might have seen something like merge sort, where I'm kind of breaking everything up, sort things, and then merge them all back together. Kind of think of it the same way. A Feistel network is basically something where I'm going to break up everything that I'm going to encrypt with a line of text, and then I'm going to, once I reduce it to its kind of like atomic subsets, I'm going to perform a series of transforms on them. In this, we are performing the AES XTS transforms. And this is really important because this allows us to create transforms on very, very small, potentially, input sizes for protection. Why is that important? Well, that's important because when we think about kind of data that we're trying to protect, sometimes we might have a small input size. So like, for example, let's say that I have Andy.com as a an email server. And if I have Andy.com, my input name, my username is obviously going to be Andy. So let's say that my email is Andy@Andy.com. That's not a huge string for me to potentially encrypt or a string for me to tokenize. So if that's the case, I need to be able to make sure that when I input that string in, that it's protected in such a way. Well, AES F3-1 is actually pretty good at this. And by using these specific types of AES transforms, what I'm doing is I'm dividing up the Unicode representation of that in such a way that I can provide a lot of security, and I can protect that entire Unicode string with these well-known transform sets in a way that is like algorithmically very fast. So the combination of Feistel networks and AES XTS transforms allow me to very quickly kind of divide and conquer a string of inputs that would be going into this, even if that string is small, because we're using the UTF-8 kind of like recognition of that string as opposed to just Andy@Andy.com. And I can then, as part of this in line with the encryption process, substitute in characters that would be ultimately defined previously, or if I note that I'm about to trip over something that has been defined as like part of my string, like for example, at the @ sign or the .com sign, I can go ignore that input. To decrypt an AES FF3-1 string requires me to be able to use a key of tweak values. Tweak values are basically guides for how, when I kind of go back to that string and I subdivide it up again, to be able to decode that information, to kind of walk my way down the potential options to be able to guide that series of transforms. So when you hear the term tweak with AES F3-1, the best way to think of it is like a string, or a key, but it's a little bit different than most keys because it's not just a big block of text. It's effectively a guide for how the system kind of walks back the information to be able to decode it. And the combination of these two kind of mechanisms ensure that I can protect very small input sizes, and I can manage a lot of keys potentially on them, because when I'm storing that data in Vault, I'm not storing a copy of Andy@Andy.com or its encoded copy. I'm storing just the key, and specifically the tweak values and other mechanisms necessary for me to be able to decode that key. So let's think about how we use format preserving encryption in practice. So, French, I cannot pronounce that, and I apologize, and out of respect to French speakers everywhere, I'm not even going to try, but French NIRs use identifiers that in the US are similar to data that we call social security numbers. If I need to manage these NIR data, I'm going to have to manage them pursuant to GDPR. And the challenge associated with managing French NIRs is that if someone gets access to this information, I immediately trip GDPR, and if my supervisory authority is in, let's say, France, they are not going to be happy about that, because I have now just committed a serious data breach, and the complications of that could actually cripple my company financially. So how do we protect this data in such a way that it's going to live outside of Vault using the Transform Secret Engine, but retain the same format, retain the same character length, retain the same alphabet, etc.? So how I do that is, first I'd mount an instance of the Transform Secret Engine. I would then encode the French NIRs or SSNs within Vault and then store them in an external database. And then when an application needs to go retrieve that data, they don't need to go immediately talk to Vault and call something like Key Value Secrets Engine. They go to the database, which is probably closer to it, and then they use Vault to decode that information. And again, this is very important. Vault is not storing with the FPE transform a copy of that data. Vault is only storing the mechanisms to decode that data. So the application is really just saying, hey, Vault, I've got this piece of information. It looks like an NIR, but I don't know what it is because I'm going to assume that it's encoded. Can you decode this for me? And Vault says, okay, hello, application. I've identified that you are who you say you are. I have passed you through all the kind of required mechanisms that are necessary to ensure that you have the right privileges to access this, both your ACL privileges, if we're talking about this just purely from the open source capabilities, and given this is an enterprise feature, also the Sentinel features that are associated with you, so making sure that if you have an endpoint granting policy for this feature, that you've validated the requirements of that, but also the role granting policies associated with the identifier. Everything is kind of on the up and up. I check it off, and we're good to go, and we decode that secret. And again, Vault isn't storing a copy of that secret. We are only storing the tweak value, the credential and kind of security mechanisms necessary to protect that data. And that's valuable for two reasons. One, the connection between the application and the database is something that could be very, very fast. So I can then focus all my time as an operator on optimizing the connection with the application in Vault for that specific kind of one-time transition. And it's a lot easier to manage than managing kind of constant or even ephemeral connections between the different applications. Now, you can absolutely do that too. And in fact, Our colleagues on the console team are very, very good at that. But if I don't necessarily want to leverage like a service mesh or something else like that, this is a very good benefit for making management of networking associated with applications and databases easier. You're using the existing kind of like networking that you have. Second, again, I'm not complicating the storage mechanisms of Vault. I'm not necessarily storing a huge, massive amount of data. I'm storing potentially millions of keys, but that's okay. Vault has already built to store and manage millions of keys. I'm not storing millions of kind of like bindings or a large file that could sitting somewhere. And so this really allows you to preserve the data architecture and networking that you have for an application, while at the same time ensuring that you protect that application with very strong cryptography. Again, if I want to go out and I go break into this database, and let's say, this actually is a very common technique, I'm going to go pop the database with like an exploit that I know for that specific type of database, dump everything in there. As an adversary, I'm confronted with something that looks like an NIR, but it's not an NIR. It is an encoded piece of information. And mathematically speaking, the process for me to decode that is just as hard as it is to protect and decode like AS256 information. So that's like all the data that's protected within Vault. And that is hard. Again, this is another heat death of the universe kind of challenge where, given even a quantum computer, you are not able to break this information in a very expedient kind of fashion. You're much more likely to have to go kind of individually talk to every single person in France and ask them for whether or not this is their social security number. And even then, assuming that you had a lot of frequent flyer miles to be able to conduct this operation, it's something that is going to take you way too long. So that's good. Again, we want to make sure that as an adversary, you are constantly confronted with this challenge where there is no side channel, there is no mechanism for you to be able to break past a vulnerability or exploit within Vault or another system to compromise cryptography. We want you to have to deal with that hard mathematical problem. And in the case of Vault, this is something that we can leverage the Transform Secret Engine for. So let's talk a little bit about some of the other applications of FPE that we've seen already in the wild. First, credit card numbers, the kind of age-old challenge associated with very, very high-speed information that needs to be externally referenceable and grows really quickly. The challenges associated with credit card numbers are highlighted by the fact that, again, this is data that needs to be protected and referenceable outside of Vault. It's of a size and scale that is far too large for a system like Vault to manage, but it also needs to be protected in a way that, that information is, let's say, proof against those complex adversaries, right? These adversaries are the adversaries that are going to go in and steal this information. If they're motivated by committing financial crimes, you want to make sure that they can't otherwise be, able to protect some of that information or otherwise compromise that information using like a complex cyber attack. This is an area for FPE to be very powerful, and because if I'm using a relational database that protects a credit card number, each credit card number has a different way of identifying that credit card number. That credit card number, if it's an Amex or a MasterCard or a Visa, etc., it's going to be something that requires me to be able to store it in a specific format. Amexes don't look like Visa credit card numbers. They look like, they have a different kind of like string size, different coupling, etc. And that challenge associated with like not being able to necessarily store things that are from different credit card number manufacturers in a specific way highlights the fact that I need to be able to protect the formatting of it. An Amex is just not going to work the same way if it's stored within a specific style or formatting that is not like an American Express credential. So that challenge associated with protecting a credit card number and protecting its formatting is very, very important, and to do so in a way that doesn't otherwise require me to compromise my ability to protect and store that information in an external database. So Format Preserving Encryption, this is a great application for it. I can protect that information such that when I need to go access that information, it is protected in that database. It's in the same database that I expect it to be, but I can just leverage Vault to be able to protect it in such a way that if an adversary was able to dump that database, they don't gain access to that information in its kind of plain text state. So that's a credit card number. Electronic medical records, and this is a challenge that is even a greater challenge in the context of COVID-19. If I need to share sensitive information, this is kind of critical privacy information that is the heart and soul of what is going on for how I would, part of GDPR. Like, this is the most privileged private information that's out there. And if I'm storing this EMR data, this PII or personally identifiable information data, and storing it and protecting it online, again, it runs into some of the same challenges that credit card numbers do. I need to be able to make sure that the application is able to access that data in a very expected format. It's going to live within the same database it's going to live, but the formatting of it might be very specific. It could be one of these kind of like social identifier numbers like we saw with the French NIR number. It could be a social security number in the United States, or it could be like a molecule, if I'm doing kind of molecular analysis or molecular surveillance and I'm trying to like share contact tracing information. So formatting is very important in EMR data, but the availability of that data and the scale and size of it are challenges such that I need to go store it in an external database. Again, this is a perfect application for Vault Enterprise. This is something where I would really want to and need to use Vault to be able to encrypt and protect that data wherever it lives outside of Vault, but at the same time ensure that it is capable to be accessible by an application and it doesn't otherwise add undue complexity to that infrastructure. Finally, the last good example of this is what we see with managed systems. So for example, let's say that I want to be able to protect a piece of information where that a piece of information is going to live in a provider that is a managed systems provider outside of Vault. So for example, I want to go store this data in the cloud, and my cloud vendor is really good. I like my cloud vendor. They're nice people. But the challenge with them is that for some reason or another, I am concerned that they might otherwise be able to unduly access my information. There are a lot of regulatory requirements that are coming up where cloud vendors need to expose access to that information to legal authorities. If I'm an international entity and I don't like that legal authority that the cloud vendor is operating in, I want to make sure that even if the cloud vendor was, compromised, that they couldn't access my information. Some of this information is very format specific. This information could be, again, the credit card numbers, the EMR numbers, everything you talked about before, or any other kind of credentialed piece of information that is otherwise very format preserving. If I want to be able to make sure that data is protected in such a way that the cloud vendor themselves or any other kind of privileged managed services provider is unable to access that information, I can leverage format preserving encryption to do that. I can leverage the capabilities in Vault to make sure that I don't compromise where I'm going to store all this data, but I'm also not going to compromise the format of it. I'm not going to make it otherwise harder for an application developer to write an application to consume that data. All they need to do is come back to Vault, say, hey, Vault, can you swap this for me? And we are good to go. So there are dozens of different types of use cases where format preserving encryption is important. And it highlights the fact, again, that when we talk about what we're trying to do with Vault, we're trying to build systems that minimize the complexity associated with protecting data. You should not be in a situation where you have to leverage the challenge and complexity associated with protecting a piece of information versus the security of the information. Security should never be a hindrance for your ability to conduct operations. And whether we're talking about format preserving encryption or the mechanisms within Vault to be able to protect any kind of piece of information, to secure security orchestration workflow, to enable you to do full disk encryption, transparent database encryption, BYOK situations for things like VMware, etc. The Advanced Data Protection Suite is really there to allow you the capability to preserve the method and style of you conducting a security operation, conducting a traditional IT workflow, or accessing information in an external database while simultaneously ensuring that data is protected. That is protected to a very, very rigorous, highly audited, and defensible mechanism of protection. And this is what we're trying to do at Vault. We are trying to force adversaries to confront cryptography while simultaneously making it easier for you to deploy cryptographic systems that make it really, really hard for them, or more specifically, to make them wait past the longer than the heat death of the universe to be able to decode that information. Thank you for your time.
Thank you very, very much, Andy. I'm absolutely mind blown by that talk. There's so many gems that you dropped in there. So thank you very much for that. I'd actually like to welcome Andy back to a live Q&A discussion panel along with Jeff Mitchell. So for those of you that don't know, these two are, for me, legends. They are foundations for how Vault was built. They're idols to me personally. I can remember before I joined HashiCorp, I was always reaching out to them on Twitter and GitHub for my issues and PRs, and they're absolute legends. So if you have any questions for them, this is your chance. They're hard people to get hold of, especially Jeff. He's a very busy person. So ask your questions in the chat below. And with that, I'm going to hand it over to Domi to kick us off with an awesome discussion ahead. Over to you, Domi.
Thank you. And welcome to Andy and Jeff indeed, especially Andy. I'm happy that I got your last name right. And good morning, I suppose. So let's just kick us off right away. You did speak about secrets, but I think it would be important to just like briefly note what secrets management is. Could you kick us off, Andy?
Or, tell you what, do you want me to take that?
Yeah, sure.
Okay, my audio is out right now. Let me try to.
All right, I'll take this question while Andy's trying to get back on track. So secrets management really is about how do you Andy went and defined what a secret is. It's anything that you want to protect that you don't want adversaries or really anyone unauthorized to see. And secrets management is really just the paradigm of how you actually deal with the mechanism of protecting the secrets. So it's one thing to say, oh well, we can encrypt it. But what do you do with that encryption key? How do you protect that encryption key? How do you gain access to it? There's a lot, like there's a turtles all the way down as an expression, and that it comes from the origin of that phrase is sort of disputed, but with this idea that at every time that you think you've solved one problem in security, like you've actually kind of shifted it to the next layer down, and you have to keep solving the problems over and over again. So secrets management really, ideally in a secrets management solution, you're finding something that tries to take care of as much of that for you as possible, so that you can focus on, on actually doing the work of, giving it a secret, getting secret back out, doing an encryption, getting something decrypted back out, and letting something else do the work of figuring out how to make sure that at every step along the way, it's defensible and cryptographically protected.
Don't tweet about work because I'd like to complain about politicians sometimes.
Amazing, thank you. So let's just kick back to the next question then. So could you tell me about how this concept of secrets management has evolved inside of the world of Vault over time? Do you want to take that one, Andy?
Sure, absolutely. When we look at how secrets management has evolved primarily through Vault, it's really less a function of Vault specifically and more a function of how the world has evolved. And historically, we've thought of secrets management as really tied to how that data is specifically supposed to be managed. So when I think about how, managing an email address, I would, originally think of it as like managing that email address or protecting the different email address in a different way that I would manage something like a credit card number or, a social security number or a name, for example. And I think what we've seen within Vault is first the evolution of us being able to make sure that the cryptographic processes to protect that data are the same. You don't need to think about like cryptography differently for protecting an email address versus a name, but also kind of like moving more towards a model where users don't have necessarily access to that information, where we minimize the possibility for employing those side channel attacks, and we maximize the ability for you to be able to continue to conduct operations. Again, use these security suites to conduct whatever you're trying to do. So in the case of like something like the email address or credential that I might be able to leverage, generating dynamic credentials or dynamic email addresses or other things that an adversary could theoretically compromise but otherwise not gain access to your infrastructure with. So it's a combination of like deploy dynamic credentials to be able to kind of like manage your infrastructure in a more safe way, combined with the fact that like I want to build one cryptographic infrastructure to protect everything and then kind of like let it up and focus on how I encode more workflows into it as opposed to changing my infrastructure every time I change an application architecture.
Amazing, thank you. So in regards to security, obviously not everybody is a security or a cryptography expert. If we hand it over to Jeff, could you tell me a bit more about what's changing in the security landscape according to you?
Sure. One thing that I've seen just as a trend from our customers over time is that we talk a lot about the crawl, walk, run journey at HashiCorp. Getting, if you think about like getting to sort of more modern workflows and more modern like DevOps and secrets management, all the sorts of things that we do, you have to start very slowly, and you have to start getting those first workflows onto new tools, and then you have to migrate more and more onto it. One thing that I've seen is that in many ways, like the things that we have built into Vault are really ahead of where a lot of companies are. We've really thought about like, what is it that you need to be able to do? Okay, so, you want to protect secrets. So, a lot of companies are starting out with just like a single basic, like we store a KV, key value secret in Vault. And yet there's so many more things that Vault can do. And so, we think of things as dynamic secrets or static secrets. So something that you put into Vault, you get it out of Vault is a static secret. Something that Vault generates for you, like a database password that it revokes over time, is more dynamic. And one of the trends we're seeing are more and more people starting to leverage those dynamic secrets, which are great because they get you more towards that zero trust model. If you're dealing with like replicated or with KV secrets, then essentially what you're doing is you're saying, I have a static thing. It might be a password, it might be like a cryptographic key, and everyone that has access to it has that same value. And what you really want to get to is a more zero trust model where you say, okay, every value that everyone has is actually different, or they never see the value in the first place. So I think that we're actually seeing people kind of catch up to where we sort of envision things would be. At the same time, I think just going back to what Andy was talking about with the advanced data protection module, I think that's us sort of like looking at it and saying, okay, we've been looking at the future for a long time, and we believe in zero trust, we believe in identity-based access, all those kinds of things. But we need to help people get there. And I think that the things that we're doing with ADP that help you do cryptography, but while keeping it in an existing database schema, or that allow you to use like legacy applications with KMIP. Those are things where we're sort of saying, okay, maybe we need to help you actually catch up to where we want you to be. Like we'd like to help you get there, but you're not there yet. So we're actually like building these things that help you interoperate with what you already have that's legacy.
Thank you so much. Just mindful of time, I think we've got loads of audience questions that come in. Rob, do we have any?
We have plenty. Unfortunately, we have more questions than we do time. So I'm just going to ask one, maybe two, and then we'll see how we get on with time. So the first one is, it seems like there's a really steep learning curve here. How much does someone really need to understand about cryptography theory to get started? Can you recommend some practical ways for getting started? I will give that one to probably Andy, because I think that's off the back of his talk.
Yeah, so when it comes to using Vault, hopefully the answer to that is none. We don't want to force you to have to sit through like years of math and cryptographic study to be able to have to deploy Vault. So when you deploy FPE, you don't need to know what an AES XTS transform is or anything else like that. Now, if you would want to kind of get into the field, there are a number of kind of really good guides and books and things you can study. Cryptography, if you're trying to leverage cryptography to build cryptographic systems, certainly there's a lot of math that you need to understand it, but you to have like a deep background in like number theory or combinatorics. Instead,
okay, it seems that we lost you again, Andy. I'm really sorry. Do we have any other questions for maybe? Do
you want me to give more of an answer
Jeff?
to that?
Yep.
I think he's totally dropped.
Go
on.
So I have another question, because I do think Andy did quite answer that from a high level. So the next question is there any guidance on data of very large sizes? So I take it they're talking about either storing that data securely or maybe transforming that data using cryptography methods that Vault offers.
Sure. So, I think it's funny. One thing that we always sort of say or keep in mind is like Vault isn't a database, even though it sometimes looks like a database. And when you're dealing with very large data sets, it really becomes infeasible to do something like put huge amounts of data, just dump it into Vault. It just isn't really built for that. However, it's very, very fast to do encryption operations. And so what we usually recommend if you have very, very large sets of data is basically to do one of two things. Either create a data key locally. So that's basically a key that you use to encrypt data locally. And then you have Vault encrypt that key for you. So in cryptography terms, that would be a DEC, a data encryption key. And then you would use like Vault's transit plugin to act as a KEK, a key encrypting key. Or just send it through Vault's transit itself, depending on how big those payloads are. But generally, when you have very large sets of data, often it is if you trust the systems that are holding those data, that are holding the data or that are working with the data, it's often better to try to push the cryptography there and then protect the key because it's much faster. You get less data transiting over the wire, which if it's that way you can avoid, for instance, if you aren't sure that you trust your connection to Secrets Manager, then you can ensure that the plain text actually never leaves the system. You just are protecting that encryption key. So generally speaking, like if you trust the systems that you're running on, you can push some of the encryption out. But if you don't, then I guess make more use of Vault directly. Hopefully that answers the question.
It does indeed. Thank you very much. I'm going to throw it back to Domi. I know we're really short on time, so I don't know if we can squeeze one more in. I'll leave that up to you. Over to you, Domi.
Yeah, sure. I think we've got a few more minutes, so we can do a few more questions. So, Jeff, in your opinion, what is the problem that everyone's trying to solve?
That's a very broad question.
Yes.
With
input.
Wow. I think that, let's see, from a general kind of high level standpoint, security is kind of a too easy answer for that. And in some ways, I think the answer is really, what are people trying to do with security? What it really is that, the modern world is complex, and it's, the more things are interconnected, and the more things are kind of electronic, the easier it is for people to do bad things. And the harder it is to keep things that you want to keep private away from outside eyes. So for instance, like it used to be that I have a document I want to keep secure. I could get a fireproof safe and I could put that document in the fireproof safe and I can have a pretty good idea that no one else is ever going to see it. Now, I may not want to trust a fireproof safe. I might want to put it, into a cloud drive somewhere where it's backed up and where I feel like it's not, one copy in one location. But now we have, adversaries that can attack and try to discover that data all along the way. So, there's one that's on my computer, there's one that's in transit to the cloud service, there's at the cloud service, there's the encryption, that protecting that channel. And it just opens up a lot of venues. And so as our world has gotten more connected, many, many things have gotten better and more simple. At the same time, they're more complex, but it's much more convenient, I guess is the way I'm saying. Like, I love our modern world. I love kind of how we can do things, electronically with computers and rapidly and all that kind of stuff. But it does mean that along with that, it opens up all these different avenues for adversaries to try to do malfeasance. And so what's everyone trying to do? They're trying to protect against that. And sometimes it's because they are, sometimes because internal secrets that would be embarrassing for them. Sometimes it's because of regulatory concerns. But regardless of the reason, that's really what it comes down to at its core, is that you want to protect your secrets, you want to protect other secrets that people have entrusted to you.
Yeah, 100%, especially as Andy mentioned in the beginning of his talk, but everything changes with the whole COVID situation, much more attack surface, I guess. Actually, I'm happy to welcome Andy back. Sorry that we've been experiencing some audio issues.
Hello.
I just, it's all right. I just heard that we have 3 more minutes. So Rob, if you've got some more audience questions, I think we are able to take them.
Amazing, thank you very much. Yes, we do. We have a few more. So we'll start with this one. Is how do you handle data with FPE that have built-in checksums? For example, credit card numbers and DL numbers must satisfy a group property. So I think we've heard from Jeff, so I'll give this one to Andy, if that's okay.
Yeah, sure. Good question. Short answer there is that if I want to do what's called convergent encryption or any other type of where I need to have a specific encoded set of information, that encoded set of information is built in such a way that I can actually have a deterministically created tweak value. So I can manage my own tweak value outside of Vault in such a way that checksum value or other kind of transform that data that's exogenous to Vault is enforced within the secret that Vault is encoding within FPE.
Brilliant. Thank you very, very much. We have one more, which is talking about storing the encryption key. Would there be a support for HSM for some of the secret engines? For example, KMIT, Transform, and PKI. This one's for Jeff.
Sure. So already if you're running against what we call an auto seal mechanism, so that's something like HSM or GCP CKMS, already we have something that's on by default. You can turn it off, but it's on by default in the enterprise binary called seal wrapping. And what we've done there is we've identified the things that are, and this is a term that comes from FIPS, a cryptographically, the moment that I say that, I lose it, a critical security parameter. And so these critical security parameters are things like what are the root encryption keys, what are the root certificates, things like that. And what we actually do is we encrypt it not only with vaults, with Vault, but we actually encrypt it with the seal mechanism as well. So if that's an HSM, then we sort of do this double encryption. And that's part of the answer, is that if what you're wondering is just sort of how can I get to higher levels of trust, that's something that we already do for you automatically by default. In terms of like, I think it's a separate question. If the question is about, I want to make use of Vault's PKI engine, but I want to have the actual signing operation done by a certificate that's in and a private key that's in an HSM, that's something that we don't have now. I think that, I don't want to comment on the roadmap because that's in the domain of product. But I would say if there are things like that you want, then reach out to your TAM or your SE and make your voice heard, and that's something the product can consider for upcoming things.
Amazing, thank you very much. And just to latch on to that, I'm always available for conversations. Do reach out to me on Twitter if you have anything like that to further discuss. Okay, with that, I'm going to throw it back to Domi.